talk about a topic on accelerating convergence. So let me see whether this is okay, let me see, go to the first page. Okay. Today I'm going to talk about scalable algorithm for Bayesian deep learning, why stochastic gradient, Monte Carlo and beyond. So this is a joint work with my student Wei Deng. So he's right now on the market. So he basically carried out most of the work I present today. So if you are hiring, I would highly recommend you considering him. And the second author is Yating Wang. She's my previous postdoc. Currently, she's assistant professor at University of Hong Kong. And Qifeng and Liao was previous Purdue students, and Georges is my previous postdoc, and also my long-term collaborator, Faming Liang here. So this is a collaborative work. So we published a series of papers on the NIPS 19, 20, and the ICML 20, SAR 21, and a series of GCD papers. So let's first go to the first part. First part, I'm going to talk about the Bayesian sparse learning with precognitive stochastic gradient Monte Carlo. So if you are interested, you can find it in our NIPS 19 paper in the GCP at 2020. So first I will give some brief introduction, then I will introduce a new class of adaptive stochastic gradient Monte Carlo. And following, I will talk about predictive SGLD and the hierarchical Bayesian models. So first, I want to talk about the motivation. The motivation is try to be able to do the async quantification for the deep neural network. The challenge facing the deep neural network is first is the over-parameterized deep neural network require heavy memory and the computational power, and it may cause overfitting, right? Also, the cost function is difficult to optimize, and a good local minimum is hard to obtain. Okay, so this is the challenge part for the neural network. So the object of this work is to do sparse learning to enhance the efficiency and the robustness and the interpretability. And because we will have a very compact neural network, so that it provides you the robustness, efficiency, and also you can look at the ways to be able to do some interpretation. And in addition, the Bayesian approach is able to capture the uncertainties, so you can evaluate like the confidence interval of your predictions from this Bayesian approach. It can compute the posterior expectation to obtain more robust results. Finally, it can escape this shallow local optimus and the settle point to achieve better point estimate. Okay, so here's some notations. So in this talk, I will using the capital D as represent the entire data set. I will using the B as a mini batch of data. And using beta to represent the model parameters, and using the L represent the log posterior densities. Okay. So the true gradient we right here is a gradient L. So we can carry out this true gradient. However, in reality, we have to using stochastic gradient to approximate using a mini batch. So that's why we're using the notation of gradient L tilde here. So you can see the compare the difference. Okay. So this is on the using mini batch, we have batch size small n instead of the capital N. So that's why we use the L tilde here to represent the stochastic gradient here. So the key components of our Bayesian sparse learning is following. So the first part is we try to do sparse learning so that we can enhance efficiency, robustness, and interpretability. And the Bayesian to capture uncertainty, we employ the empirical Bayesian method to learn a class of hyper-Bayesian models, so yield a data-driven adaptive penalties. And to do the training, we're using the adaptive stochastic gradient longitudinal dynamic, or we call it SGMCMC, to capture parameter uncertainty and avoid overfitting, and also escaping the shallow local optimum and the settle point, and compute posterior expectations. Further, we developed this so-called preconditional SGLD to update parameters with different step size and adapt to local geometric and resulting in a faster convergence for components of beta have different scales. It's very suitable for solving a heterogeneous media multi-scale problems. And later, we also included this stochastic approximation approach to optimize latent variables in prior. So to convergence to the asymptotic correct distributions with controllable bias. Finally, we developed the pooling strategy to enable a sparse deep neural network. Sparsity is ensured, resulting in less usage in memory and computation power. So this is SGD, so we're not going, so everybody knows. So, so we need to find the map for model parameters through the stochastic optimization. But the drawback is it do not capture parameter uncertainty and it can potentially overfit data. So that's why motive is to develop this variation of different kind of form of a Langevin dynamic. So a Langevin diffusion with a stationary distribution can be described by the SDE, this d beta equal to the gradient L dt plus square root of dw. The dw, the w term is a Brownian motion term. So we can using the Euler discretization of this equation 1, approximate the true gradient by the stochastic gradient, we represent by the equation 2. You can see we replace by a Gaussian distribution here. And the equation 2 is symptotic conversion to a distribution that proportional to e to the tau times the L. The tau is represented as 1 over the temperature. So tau is increasing. So this epsilon k decreases. The solution tends to the global optimum with a higher probability. So the advantage of using this stochastic gradient Langevin dynamic is it can sample the neural network posterior to model uncertainty and also compute the posterior expectation to obtain more robust results. And also escape local optimas to achieve better point estimate. The SGLD update all parameters with the same step size. This may cause slow mixing when components of beta have different scales. That motivates to develop this so-called preconditional SGLD. So also we optimize the prior with stochastic approximations to improve the efficiency. So there's several approaches we developed. If we want to improve the efficiency of sparse sampling, we can infer prior from empirical data and then learn prior through optimization instead of sampling and ignore uncertainty of prior to speed up inference. So we optimize prior by the stochastic approximation approach. Basically, we optimize latent variables without affecting the convergence to the symptotic correct distributions. So the basic idea of stochastic approximation is the following. So we intend to solving the root of the integral equation, the equation 3. Here, this H is a bias estimator to the mean field function H theta, where K is finite but asymptotic unbiased as K goes to infinity. So this stochastic approximation algorithm has 2 steps, and it's also an iterative recursive algorithm. The first step is we sample the beta K. The beta is the hyperparameters in the neural network. So basically we sample the beta from the transient kernel, which admits the F theta as the invariant distributions. Then we update the parameter inside the prior theta K plus 1, okay, using this the biased estimator of the mean field function. So that's the 2-step approach here. We develop a class of adaptive stochastic gradient MCMC methods. So here, first we develop the first order stochastic gradient MCMC. Okay, it's basically a sampling algorithm which asymptotically converge to a stationary distribution. So, and also for the adaptive SGLD, we introduce the auxiliary variable theta and formulate an inhomogeneous Markov chain. So you can see we add this theta here, okay, so that it can do some adaptivity here. Where this eta is basically satisfy a normal distribution, okay. So the eta here is the learning rate. The H is biased by asymptotic and biased estimators, okay, of the mean field H. Okay, so that's we do this SG MCMC, and then I will talk about the pooling strategy to enable the sparse deep neural network. So what we did here is we apply the magnitude-based weight pruning to our compression experiments. So the weight pruning, basically, we set up a threshold. So if the weight is over some threshold, we keep it. If it's below, we throw them away. So the weight pruning can also be viewed as a greedy L0 regularization in the optimization. So by doing this, we can obtain a sparse neural network. So the following, I'm going to talk about the predictional SGLD. I've told you that the motivation to do this is because we want to update the parameters with different step size and adapt to local geometric, and resulting in faster convergence for components of beta have different scales. That's the motivation we want to do here. So it's the theoretical background of predictional SGLD is come from the Langevin dynamic in Riemann manifold. So consider the family of the probe distribution lying on Riemann manifold, for which the expected Fisher information matrix defines a natural Riemann matrix tensor. So here, if you look at the SDE define the Langevin diffusion on a manifold, the G is the manifold metric tensor. And if we take the gradient of G, we get a tau. So, and then we add a tau into here. So you can say this is the difference compared to the traditional Langevin diffusion. It has an actual tau term, and they have this the G term here. So then we can do the Euler discretization of the equation 6 using stochastic gradients. So we can discretize the equation 7 here. So in fact, adding positive definite matrix G inverse define a value Riemann manifold. So we are not restricted to using the G inverse beta equal to I beta. We can choosing a different kind of G inverse to do, as a preconditioner. So here is the iterative steps. So first we define the G as a diagonal of 1 over lambda I plus square root of V, and the V is iterative. So at a V beta k equal to alpha V beta k minus 1 plus 1 minus alpha G beta k dot G beta k here. So you can say the G is basically the gradient of the, So we develop a hierarchical Bayesian formulation for sparse inference to encourage the sparsity. So we're using the spark and the slab Gaussian Laplace prior so that we can gain this sparse posterior. So here I'm basically showing you the preconditional SGLD with the stochastic approximation pseudocode here. So within the loop, first we obtain this G beta k approximated by the gradient of Q. Then we updated this V by using this iterative step omega k times the V plus 1 minus omega times G dot G. Then we updated the capital G beta, okay, equal to this inverse of the diagonal matrix. Then we updated the beta. Then we do the pruning. Okay, if you define the pruning, the bottom as percent weights with a lowest magnitude, then we can greatly reduce, okay, the very small weights, then get a sparse matrix. Okay, then we do the loop. Okay, so that's the basic steps of the predictional SGLD. The following, I'm going to show you some results. So consider a data set. We do a simple regression problem that's a y equal to x beta plus eta. So we have the n equal to 100. So and the p equal to 1,000. Okay. So this is a large p small n regression problem. So we have 3 parameters. One is basically the beta, right? So we want to estimate beta, eta, right? So we want to estimate and the sigma here. So you can see, so in the bottom, so basically look at this black is the true value, and this blue one is our method. So you can say our method can obtain the true, very close to the true posterior distributions, and the other, like for example, the SGLD way over, compared to the true posteriors for these 3 different parameters. So our method all be able to capture the posterior distribution well. And also, if you look at the spread of the data, right? So you can see the black is the true value. So our method can very close to the black dot, the blue dot very close to black dots. Okay, but the other, for example, the red one is spread out, cannot capture it accurately. Okay. So let's look at what the advantage of this method in the network compression. So if you look at our proposed method, so on the top, if you look at the table, so we use on ResNet 20 compression on the C510 dataset. So if on the first, on the table, if you look at the first row, it's S represent the compression rate. So on the right, if you look at the 90% compression rate, that means we throw away 90% of the weights, only keep 10% of the weights. So that makes it the network very compressed. And however, if you look at the accuracy, we still can preserve 91.68 accuracy. So for C510, we can achieve the state-of-art accuracy. We can using only 27K parameters with 90% sparsity. We can achieve 91.68% accuracy. If you compare all the literatures, for example, 2018, the people using dropout, they can achieve 91.48% accuracy, but however, they need to double the number of parameters to achieve the same accuracy. Okay, so this already state of the art. So you can see our method can achieve a much better network compression and preserve the accuracy. Okay, let's look at the small n large p problems using the preconditional SGLD. So if you're using the rare one represent the preconditional SGLD, you can see we achieve a better than other two benchmark. Okay, so if you look at the black one is true, our method can overlap with the true posterior distribution very well for the beta 1 and beta 2. Okay. So we're testing the MSE arrows. Okay, so if you look at the MSE arrows for during the iterations, so you can see the black line is our preconditioner approach. It can converge much faster than without the preconditioner. This yellow line is without the precondition, so we can achieve much faster convergence here. Okay, and I want to show you some more difficult problems, such as the multi-scale flow equations. So let's look at a multi-scale flow problem. So this the kappa inverse times u plus gradient p, okay, equal to 0, then we have divergence equal to f. So then we want to basically, traditionally people using on a fine grid using the mixed finite element approach, then also using the velocity approximation, normally people using RT0, okay, for the pressure, people using P0 finite element to solve it. And the difficulty is that the AH is large and it depends on the kappa. So we want to using the neural network to learn the structure of the kappa and obtain the multi-scale basis. So this is the basic idea. So we want to develop a so-called multi-scale model reduction. So we want to mimic the standard multi-scale finite element approach in the restriction and prolongation approaches. So the difficulty using traditional approach is the multi-scale velocity basis usually needs to be recomputed when the kappa changes. Our goal is design a sparse learning algorithm to achieve efficiency and maintain accuracy here. Okay, so basically is you give me a kappa. So if I have a neural network, I can predict the solution of U. Or if you give me a right-hand side F, I go through my neural network, I can predict the solution of U. So here is our convolution multi-scale setting of this problem. So you give me a kappa, so I will go through this upscaling, go through the convolution, pooling, flattening, then dense reshaping, and then we go through the convolution flattening, then we can downscaling again, right, to predict the solution. So that's the architecture of this one. So we want to learn the feature through these convolution steps, and using that to do this model reduction. So here I want to show you some numerical results using this approach. So in the dense neural network, we need over 6 million number of parameters to carry out this prediction. However, if we using this 70% sparse rate, we only need a 758K of parameters. That's almost like only 10% of the parameters we keep for the neural network. However, if you look at the accuracy, so this is the E1, E2 are basically the MSE, E2, this is the K norm. So you can look at basically using these two different norms, you can see even with a 70% reduction, we still can keep very similar accuracy. Okay, so but we only using 10% of the neuron. Okay. Also, let me show you some the learning curve with different convolutional representations. For 128, is the problem has higher dimensions, basically 128 dimensions. If you can take a look at the problem, so you can see our predictive approach can achieve much consistent and faster convergence. And if we look at this with true versus prediction, so on the left column is the true prediction of the velocity field. On the right is without the preconditioner. The middle one is with precondition. So you can see, apply the preconditioner can capture the structure very well. However, without this preconditioning, it has a lot of noise. Okay. So this is the convolutional representation of 32. This is 64. You can see they have a more fine scale structure, but we still using preconditioning approach, we still can capture it pretty well. If we increase in the dimension to like that 128, you can see it has a lot of finer structures. Our approach still able to capture, the fine structures. But however, if you look at the without application, it's totally blurred. Okay, so here's a summary of the first part is we propose a class of adaptive stochastic gradient MCMC approach with wider applications and prove the convergence. And also it can be applied to the empirical Bayesian method to learn a class of hyper Bayesian models and the yield driven adaptive penalty. And also we propose an adaptive Bayesian sparse deep learning algorithm for regression problem. And also we optimize the prior through the stochastic approximation. And we sample with a preconditional SGLD, which can adapt to the local geometric and results faster convergence. Okay, and the convergence to the symptotic correct distribution with a controllable bias we introduced by the stochastic approximation. And here's some reference I'll go through quickly. The second part of my talk is about accelerating convergence of stochastic gradient MCMC, why replicas change and beyond. So this work is also carried out mainly by my student Wei Deng. Let's look at what we do here. So first I will just go quickly about some background. And because asynchronous quantification is crucial for AI safety problems and reinforcement learning, so which draws our attention to using MCMC, which is known for multimodal sampling and the non-convex self-optimization. However, MCMC has some drawback and limitation. We want to speed up. That motivates to develop this series of methods here. The multimodal sampling can accurately predict the confidence intervals, and also it can achieve better point estimate. And we approach this problem using a Langevin diffusion. So a famous sampling algorithm is called the Langevin diffusion. So the d beta t is equal to minus gradient u dt plus the square tau dwt. Okay, the beta t is the parameter time t, and u is energy function, and wt is the Brownian motion, and the tau is the temperature. So as t goes to infinity, the beta t converges to the stationary Gibbs distributions. And here the tau represent, like you can see, so if we increasing, okay, the tau, the distribution will become flatter and flatter. Okay, so that's so they can see the difference here. So we can control the tau to achieve different purpose of speed up. However, evaluated gradient is a big problem, and it's very computationally expensive. To tackle this issue, so Max Wellin proposed the stochastic gradient Langevin dynamic. So it's basically introducing the beta k plus 1 equal to beta k minus the eta at its learning rate. The gradient u tilde means the batch size approximation plus a normal distribution. As t goes to infinity and eta goes to 0, the beta converges weakly to the stationary Gibbs distributions. And let's look at this movie and show a multimodal distribution using stochastic gradient Langevin dynamics. So let's see whether I can play it. Let me see. Yeah, seems I cannot play. Yeah. Let me see. It seems I cannot play. Anyway, so I can move. Okay, I know what I do. I need to. Okay, I think Now I should be able to play it. Okay. Let me see. Let me do Control L. Okay, so now you can play. I don't know. Okay, so you can see it's we started this SGLD. We have a lot of local minimum here. You can see it. The blue points can jump from one local trap to another local trap, right? But very slowly. You can see it has the capability of jumping out of the local trap, but but in the middle is the global minimum, right? But however, it has to do a lot of sampling to be able to find out the global local minimum. It takes a lot of time to get a converge. Eventually, it's gonna converge, but takes a lot of time. So that's the showing you what happens if you're using SGRD. So that's motivated to develop some strategy to accelerate MCMC. The several different approaches. The first one is simulated annealing in 83. And the second one is the replica exchange MCMC by Swenson and Wang in 86. And so that's motivated to develop this replica exchange SGLD we published at the RCML 2020. So the basic formula is we consider two Langevin diffusion process. We're using two different temperatures. So the first equation and the first equation, we have a tau1 larger than tau2. So we have these two Langevin diffusion, and we want to swamp them. Okay. So the position of the two particles swamp with a probability S. So they satisfy this distribution with the e to the 1 over tau1 minus 1 over tau2 of this two energy function difference. In other words, a jump process is included in a Markov process with a probability here. The R is the intensity rate times the swamping. So then there's this inverse of the probability is basically 1 minus this R times S. Okay. The basic idea of philosophy behind this replica exchange is try to using the high temperature to do this red line, this high temperature. So we want to using the red curve high temperature chain to explore the whole landscape. And once we find some good point to start with, then we switch to this low temperature one to do the exploitation. So this way we can take advantage of both high temperature and low temperature, because high temperature is good at exploration and low temperature chain is good at the exploitation. So we combine the both advantages so that we can find the global minimum very fast. So that's the motivation we try to use in the replica exchange. So that's basically this figure show the trajectory plots of for replica exchange of Langevin dynamic. So why the naive numerical algorithm fails, right? So here, basically, if people just naively using the traditional replica exchange approach for this stochastic gradient Langevin dynamic, they will fail. So let's look at why. Because if we using this, consider using a stochastic gradient Langevin dynamic with two temperature, tau1 and tau2, if we swamp the chain with a naive swamping rate, the R times S, with beta theta, and yeah, so then the explanation the unbiased estimate L theta will lead to a larger bias is because we're using a small batch size. Okay, that will lead to that's a large bias. To solve this problem, so we have to do some correction terms. So if we look at this L theta, satisfy a normal distribution, and consider this geometric Brownian motion in each swamp as a martingale. So we can represent this S theta as an exponential term included this geometric Brownian motion term here. So take the derivative of the S theta. So we can represent the ds theta equal to the square root of 2 times 1 of tau1, this two temperatures for this two chain, 1 over tau1 minus 1 over tau2, okay, times delta S theta, then by fixing t equal to 1, we have the suggested unbiased swamping rate. That is, we need to add this orange term so that to do the correction. Okay, so that's the, we want to add this correction term. So let's look at some movie to show you the replica exchange stochastic gradient versus the right is the replica exchange, the left is traditional SGD gradient. So let me show you that. Okay, so let me first show you this replica exchange. Okay, so let's see whether it can play. So you can see the right one can go to the middle very quickly. You can see it's swamping much faster than the traditional SGLD approach. It can explore the landscape very fast. It can go over to the middle, because the middle is where we have the global minimum there. Okay, so you can say without the knowledge, right, of where the global is, it can explore the whole landscape very fast. Okay, so that's our using this proposed replica exchange approach. You can show much faster convergence. Here, I want to present some convergence analysis of the replica exchange as GLD tracks the replica exchange Langevin diffusion. Okay, first, this lemma is to present you the discretization error. So given the smoothness and the dissipative assumption in the appendix of the paper, and a small learning rate eta we can the expectation of the soup of the beta t, the true beta t minus the beta t approximation, okay, small batch approximation, is bounded by eta, is learning rate, and the maximum of expression of phi norm square, 2 norm square, is the phi is basically the noise in the stochastic gradient. Okay, plus, okay, a maximum of square root of expression of psi square. The psi is the noise in the stochastic swamping rate. So basically, you can see it's controlled by 3 things, right? The first thing is the learning rate. Second thing is the noise in the square gradient. The third rate is affected by the noise in the swamping rate. So that motivated, later on, I will introduce about the variance reduction approach. Is we want to reduce the noise in the stochastic swamping rate. Okay, so the convergence of the replica exchange SGLD is controlled by 3 things. Okay, so here's our theorem of convergence of replica exchange. SGLD, let us smooth the dissipative assumption hold for the distribution mu k associated with the discrete dynamic of our parameter beta k tilde. We have the following estimate for k. So the Western distance of the mu k to the target distribution pi is less than equal bounded by these 4 terms. The first term is d0, some constant, okay, here, the representative of d0 here, times exponential term. The exponential term, inside the exponential term, we have this delta s here. The delta s is the acceleration effect, okay, depending on the swamping rate s. Then plus the square root of the learning rate, and plus the maximum expectation of the phi I represent noise of the SGD, and plus this maximum expectation of psi I, this is the noise in the swamping rate. Okay, you can say it depends on these 4 terms here. Then I'm going to show you some numerical results. So here I basically presented comparing the SGLD versus replica exchange SGLD here. So if you look at it, you can find out that on the top black line is SGLD, and in the bottom one is the acceleration using replica exchange. On the x is the k, the iterations, and the y is the Washington 2 distance compared to your current distribution of beta versus your target distribution pi. So you can see the replica exchange can achieve much faster convergence. Okay, so can we do better, right? So that motivated to develop some better, faster replica exchange algorithm using the variance reduction. So that motivated to develop this another work on the exponential acceleration y variance reduction. Yeah, published at ICLR 2021. So to accelerate the convergence using the variance reduction, the motivation is to obtain more effective swamp drivers to design more efficient energy estimators. To reduce the variance of the noise energy estimator, so we're using the L equal to the capital N is total number of samples, and divided by n, and small n is the batch size number of samples, okay, little n here. So I'll have the H and equal to from 1 and 2. The 1 represents the chain 1, 2 represents the chain 2. So we obtain an I-bias estimator of L, right? So and a constant C. So we set this new estimator we can represent by a control variate. So this C is a constant, so we can optimize the C to obtain the optimum performance. So the L tilde, if we apply the control variate, so we have, so L tilde equal to this L plus C times this L minus the summation from I equal to 1 to N, okay? So the second term is basically a surrogate estimation of, of the beta, of the energy functions, okay? So the whole thing we can prove is still unbiased estimator. By decomposing the variance, so we do the variance decomposition. So we find out the variance of L tilde equal to, this is 3 terms. Then if we want to, the variance of on the left-hand side to be 0, then we can derive the constant C, right? So in such case, we can obtain this C star, right? The C star is equal to minus the covariance divided by the variance. Okay, so this is basically just standard control variable approach. So if we apply here, so we can obtain this optimum constant C. By doing that, we can achieve reduce the variance of the estimation. To make a variance reduction work, it requires 2 crucial steps. The first step is to propose a correct control variate beta hat. And we approach it by update the beta hat through every M iteration. We do a kind of a global estimation of the beta H, okay, to do the updation, to build a surrogate. And the second is we need the optimal C, okay, is unknown. So that's why we have 2 approaches. The first approach, we can set C equal to just -1 for highly correlated energy estimator, or more advanced approaches, we set adaptive C for the less correlated cases. So here, this variance reduction replica SGLD leads to a more efficient energy estimator with a much smaller variance. So here's the lemma about the variance reduction energy estimator. So under the smooth and the distributed assumption, so the variance of the variance reduction energy estimator is upper bounded by these 2 terms. One is controlled by the M square. M is like how many steps. The step size you want to do the variance reduction. Okay, the eta here is the learning rate. The little n is your batch size, the number of samples inside each batch, and also the variance of this the total number of n divided by the each batch number of n, then do the summation of the L energy, basically energy estimators approximation, and it's a variance. Okay. And so therefore, we can have this variance reduction for large swamping rate. So basically, given a large enough batch size n, the variance reduction estimator yield a truncated swamping rate that satisfies the following. The expectation of this swamping rate is the minimum of 1 and the S of the beta 1 and beta 2 of 1 over n squared plus the exponential of minus this n squared eta or n plus 1 over n squared. So this basically tells you so like how frequent we estimate, right? So we can achieve better accuracy. Okay, so that's, I will show you some examples here. So here basically want to show you is we using do a comparison of 3 different methods. The X is the K, the Y is the Washington 2 distance of the mu K, is our target, our estimated distribution of beta versus the target distribution pi. If we compare these 3 methods, so the black line is SGLD, and the blue line is the replica change SGLD, and the red one is the variance reduction, that's the replica change. So you can see by using this variance reduction, it can achieve further speed up, okay, and then faster convergence than the other 2 approaches. And here, let's look at some results. We're looking at the A is our parameter beta 1. If we look at the tracing plot, although this beta 1, you can see it has 2 modes, right? So the red is ground truth, and the blue is the variance reduction approach. You can say they overlap each other. So even it has a multimodal distribution. So our approach can to capture these two modes very accurately. And for the second one, you can see if we compare to the SGRD with our replica exchange, right? You can see red one is a ground truth. And if we're using the SGRD, it only can capture one mode. And if we use replica, it can capture this both two modes very well. The third one we look at is different M. So if the red one is M equal to 15, okay, and so basically the blue one is M equal to 50, and the green one is M equal to 100. So you can see a smaller M resulting in smaller variance, okay. So the Y coordinate is just log of the variance, okay, square, the log of variance. X is just number of iterations. So you can see smaller M means I do the variance reduction more frequently. Okay, so then that way I can reduce the variance more dramatically. So that's why we observe the smaller variance. Okay, so that's agree with what we say in our approaches. And so if you don't do anything, just the black line, okay, just replica exchange, it has a larger variance here. The last one, we basically showing you the contour of this log of the variance versus of your learning rate, of your batch size. Okay, so the X is your learning rate, Y the D sub figure. Okay, so the X is learning rate in log, and the Y is your batch size. So you can say that the number of samples inside each batch, if you increase it, you're gonna achieve a smaller variance here, okay? And if you reduce your learning rate, you also can achieve a smaller variance, okay? So this is just showing you two factors gonna affect your variance, okay? And here, this plot I want to show you is the variance reduction on the noise energy estimators on the CFI 10 and CFI 100. So you can see M infinity means like we almost don't do any variance reduction, right? So so if M equal to 50, so you can see on the larger data set, right? For the smaller data set, you can see you do you apply the variance reduction, the effect, you don't see much gain unless you do in the later iterations. However, that's because this simple problem, right? All the method works. But however, if you look at more challenging problem on the CFI 100, it's higher dimension problem. And then if you look at apply this variance reduction at M equal to 50, it can dramatically reduce the variance. You can see here, okay, the second plot, B. The same thing happened to the variance reduction setup for M equal to 50, 392, okay, in the C and the D, it's similar setting. Finally, I want to show you the accuracy. So using, we have developed a different version of a variance reduction approach. So you can see compare on the CFA 10, CFA 100, on the ResNet 20, 32, ResNet 56. So we all can achieve still at the best performance compared to the other approaches. The M, it means momentum SGD, stochastic gradient, Hamiltonian, Markov chain, replica exchange, variance reduction, replica exchange, cyclic SG, Hamiltonian, Markov chain, our cyclic variance reduction, replica exchange SG, Hamiltonian, and Carlo. So you can see all these different approaches we have compared. So our method is still state of the art. And also I want to show you the non-conveyor optimization on the CFA 10 and CFA 100 on the using the adaptive coefficient. So you can see by applying this adaptive coefficient, we can achieve almost like 1.5 accelerations, okay, by using this adaptive coefficient versus non-adaptive coefficients, right? So you can see we do be able to gain some speed up by using the adaptive procedures. But however, when you epoch increases, right? So the effective of this using the adaptive coefficient will drop close to like 1.1 something, So this basically you gain a lot in the beginning. This basically I want to deliver the message. So here's a summary. So basically, we're introducing replica change stochastic gradient MCMC show a potential in exponential acceleration in the convergence in non-convex learning. And also the variance reduction of energy estimator yield exponential more effective SWAMP, which further accelerates exponential convergence in a non-convex learning. And this is the first work to do variance reduction on energy estimator in deep learning, which paved the road for accelerated advanced stochastic gradient MCMC algorithm in non-convex learning. Yeah, thanks for your attention. Yeah, I'm open floor to take some questions. So here's some reference. Yeah, Ralph, please. Algo.
Hi, Guang.
Hey, Algo,
Thank you very much for the talk. Really enjoyed it. I have a quick question.
Sure.
I'm actually not sure it's quick, but can you, it seems to me that during replica exchange, so imagine a situation where you have a convex problem, not a non-convex problem. In such a case, replica exchange will not be useful. Whereas in a situation where you have lots and lots of local minima,
yes,
it seems to me that replica exchange will be very useful.
Yeah, I agree with you.
I'm wondering if your theoretical results somehow reflect this. In other words, is there, does this difference show up as to how many local minima are present and what its effect is in terms of replica exchange being effective?
Oh, okay. Yeah. I think that's yeah. I think you raise a very good question, right? It's also a challenging question, right? I would say. I think that might be so. Yeah, I think that we need. I think yeah, this is a kind of so what we are doing is basically we change this thing to be a kind of sampling approach, right, instead of optimization, right? So then we estimate the energy. So I think maybe your question like more related to, for example, how do we represent this the multi-mode energy, whether the energy landscape is rough or just single mode, right? How do we represent it, right, in a way so that we can put it into the error estimator to represent maybe the roughness, the smoothness of the energy landscape, right? We use some metric to represent and put into the error estimator. Maybe that's one of the kind of approaches we can use. Right. I think that's definitely a good direction. What you, yeah, it's a good question. I think it's worthwhile to look into it to kind of, yeah, to represent in a more, look into more details. Yeah, I agree with you.
Thank you.
Yeah, Hajal, your questions?
Hi, thank you very much for the nice talk. I just want to ask a quick question about the numerical examples. So in all the figures you saw us, you compare the convergence speed for about order 100 epochs. And actually, when you saw the numerical numbers for the accuracy, how many epochs did you use? Okay, do you can you tell us some comparison when the optimization after like 10,000 maybe probably people might use 10,000 epochs.
Yeah.
Get the results. Can you tell me the result?
Yeah. I think my student Wei-Deng is here. So Wei, can you address Hajal's question?
No problem. Can we go back to the experiment part?
You mean here or here?
Yeah.
Here.
Maybe the next slide.
Next one. Next, you mean? Yeah.
For the table.
Oh, here. Okay.
Yes. So, Professor Yang, can you like elaborate your question again?
So typically, I assume that to get this result, you may take like 10,000 epochs to get results.
10,000 epochs? No, we just use like 500 or 1,000 epochs. 500. Yeah.
Okay. So my experience that when I use deep learning, the number of epochs might be very large, and if we compare the curves of different optimization algorithms, sometimes some algorithms might converge faster in the first few iterations, but after that the performance might be quite similar. So I just wonder the performance after like 500 to 10,000.
Okay. For me, I think what all it matters is about the learning rate. You know, when we use a larger learning rate, we're gonna do the exploration, and when we use a smaller linear rate, we're gonna do the exploitation because the noise in the smaller linear rate will be smaller, right? So it basically, this somehow inspires us, like we need to use a very large linear rate and run it for a very long time. And in that case, we have a larger probability to hit the more promising region. And that's why in the later period, it's not that matter at all. I think all that matters is the exploration period. If you explore it sufficiently well, and then you decrease your linear rate immediately, just using a very short period. In that case, you have a very large probability to hit a very promising region. And I feel like, although we may see some similar patterns in the later period, all it really matters is the previous period when we do the exploration. So I feel this is kind of the difference.
So do you mean that learning rate is more important than algorithms?
Actually, you know, this algorithm can be adapted to that algorithm. For example, for two replica, and if we will SGD with constant linear rate as a Monte Carlo method, then SGD with a larger linear rate is the exploration chain for the replica exchange, right? And the SGD with a smaller linear rate is the exploitation chain for the lower temperature process, right? So somehow they have to exchange, and linear rate is more important. And in Monte Carlo, temperature and both linear rate are both important. So yeah.
I see. Thank you.
Yeah. Okay. So Jianfeng, you have questions? Yeah.
Yeah. So actually, kind of related with the answer for the previous one. So I'm slightly worried that if you using two different discretization parameter for the two replica, and also there are all these like stochastic gradients involved, right? So can one say something about the invariant measure? I mean, because it's not entirely clear to me that the invariant measure is preserved, or I mean, whether the error can be controlled.
You mean the W2 distance, or what kind of error?
Yeah,
I mean, not finite step, but I mean, like, what's the invariant measure of the process?
I think if we use a constant linear rate, there will be definitely a bias associated with the discretization.
Yeah, but I think you mentioned that you're using different learning rates for different replica, right? So that seems to be a bit dangerous to I mean, could that mess up the invariant measure? Okay,
I understand your question. And actually, I have thought about this question before. And I feel like, and I have done a simple experiment if we use two replica with two different linear rates, and the result is it's still the same. My understanding is like, for example, we use a larger linear rate for one process and use a smaller linear rate for another process. Then if we become careful about the swapping rate calculation, then let me see. Well, yeah. First of all,
it's like that you have the usual replica exchange, right? But then you are multiplying one of the replica, the gradient, by a constant number. I mean, one can think in the SDE level like that, right?
Yeah.
And I mean, I mean, I haven't done any calculation, but that seems indeed a bit slightly dangerous. But maybe it's okay. So I'm just wondering whether you have thought about it.
Yeah. How about we think about it in this way? Like we use a larger linear rate for the low temperature process and use a smaller linear rate for the high temperature process. In that way, if we split the larger learning rate for the low temperature process into two parts. One part is for the same learning rate compared with the high temperature process, and another is just a process without the swap. So in that way, the environment manager can be comparatively the same. So because your question is indeed quite promising, because I ever thought about this empirically, because we are very interested in different learning rates, and I indeed have done some experiment to support my conjecture, and the answer is, if we use different learning rates, at least in simulation, it's still the same. Maybe theoretically there are some slightly difference. But
yeah, we can discuss about that later. I mean, I think one can actually see theoretically what the effect is. I mean, yeah, I'd be happy to talk later.
Yeah, John,
thank you for your question.
I just want to comment on Jian Feng questions, actually.
Okay.
So if I understand it correctly, right, you are trying to learn the invariant measure of a gradient system. So by changing the learning rate, it seems to me that you're pretty much just perturbing that stochastic dynamics, right? So then your question probably can be postulated as whether, when you change this around, whether you're still going to converge to the underlying invariant measure associated to the appropriate ergodic measure. I think, is that correct?
Yeah, it could be even worse, right? Because by multiplying one component of the gradient by some number,
right,
you could also destroy the gradient structure
of course.
So it's actually a bit non-trivial.
So basically, I think the answer to your question probably has to go back to the paper by your colleague, right? Mattingly, Stewart, and so on. They have a paper where it just basically depends on what is the global Lipschitz or local Lipschitzness of the vector field, and then when you make this perturbation, whether you still satisfy all of this condition for ergodicity, geometric ergodicity of the underlying dynamics. I think that's the lead to do that. If I may comment.
Yeah. I think it's a good. Yeah, thanks for the good comment.
Can I interrupt for a little bit?
Sure.
I feel like the geometric ergodicity won't be affected a lot. But anyway, I feel this is a very enlightening question. Thank you.
Yeah. Okay. Yeah. Sounds good. Okay. So maybe so we just we need to move on. So let's say our